It's not a comet, and it's not from here. Just months ago, 3I/Atlas was a greenish blur on the edge of the solar system. Now it's racing toward the sun at nearly 70 kilometers per second, shrouded in a coma so vast it dwarfs planets, and turning an ominous deep red along the way. But here's what no one expected. Its shifting colors make no chemical sense. Its glow moves from red to green, without warning, and the core, completely hidden, anywhere from the size of a city block to a mountain. If 3I/Atlas just turned reddish, what does that reveal about its true identity? And what are we actually witnessing as this alien traveler barrels toward Mars and the sun at this very moment? 3I/Atlas is moving through the inner solar system at nearly 68 kilometers per second. That's over 240,000 kilometers every hour, fast enough to cross Earth to the moon in less than 90 minutes. For comparison, that's about twice the orbital speed of Mercury and more than 10 times the closing velocity of most long-period comets. This is not a slow drift through space. It's a kinetic jolt, a visitor from beyond the sun's reach, plunging inward with energy that dwarfs anything in the planetary neighborhood. The trajectory is hyperbolic. Its path is not bound to the sun, just passing through on a one-time visit. The inbound speed rules out any possibility this object originated from the Kuiper Belt or Oort cloud. Only a true interstellar traveler arrives with this much momentum. As Atlas barrels in, solar radiation slams into the coma, stripping material and charging particles at a rate rarely seen. Every second, it covers a distance equal to the width of a small country. These are not numbers we see in ordinary comet science. This is something else. A body moving too fast, too straight, and too powerfully to fit the mold of anything born inside our solar system. The invisible core, wrapped around 3I/Atlas, is a dusty envelope, so vast it nearly defies imagination. Even the most powerful telescopes, Hubble, Gemini, the Nordic Optical, show only a faint glowing shroud. The coma expands outward for thousands of kilometers, overwhelming any trace of the object's solid heart. At best, high-resolution imaging places the core at less than 5.6 kilometers across. But some estimates go as low as a few hundred meters or as high as 50 kilometers. That's a spread of more than 2 orders of magnitude. The nucleus is dwarfed by its own outflow, hidden inside a haze that could be many times wider than Mars. This is not just a spectacle. It's a measurement problem. Every attempt to pin down the core's size runs into the same wall. The coma outshines the nucleus by orders of magnitude, scattering light and masking the object's true shape. Even with the best data, astronomers are left with a range, not a number. If the core is small, it would be one of the tiniest interstellar objects ever caught. If larger, it could rival the biggest known cometary nuclei. Until a spacecraft or a perfectly timed occultation reveals the interior, the heart of 3I/Atlas remains a mystery, fueling debate over what exactly we are witnessing and what to even call it. The first polarimetric images arrived in late July, and within hours, the data set off a storm of speculation. Dr. Toni Santana-Ros and his colleagues had just finished calibrating exposures from the Nordic Optical Telescope. They expected the usual diffuse haze, random, featureless cosmic fog. Instead, the maps plotted as a clean, steep curve with a negative branch that dropped lower and sharper than anything in the catalog. The degree of linear polarization reached minus 2.8% at just over 6 degrees phase angle, a value more often seen in distant centaurs than in comets. The inversion landed at 17 degrees, again matching objects in the outer solar system, not the inner zones where comets typically roam. Santana-Ros remembers a moment. We had barely enough nights to catch the coma's signal before it evolved. Each new image changed the story. But as the team searched for rumored concentric bands, the maps remained stubbornly uniform. No rings, no double-layered shell, just a homogeneous field. Cross-checks with the very large telescope in Chile and Rosen Observatory in Bulgaria confirmed it. Any variation in polarization was below 0.2%, well within instrumental noise. The absence of ordered rings didn't diminish the shock. The phase angle behavior alone set Atlas apart. The negative branch pointed to dust grains larger and darker than those in typical comets, possibly aggregates laced with organic compounds, and ices shaped in the coldest corners of space. Models built for solar system comets failed to reproduce the curve unless they borrowed parameters from trans-Neptunian objects like Pholus. The evidence was clear. An object that looks like a centaur moves like an interstellar visitor and scatters light in a way no comet has before. And Part 1. Part 2. The dust that shouldn't exist. The polarization curve signals the presence of large, irregular aggregates. These aren't compact, bright grains familiar from most comets. Instead, they are loose, porous clusters woven from organics and ice. Their structure more like tangled webs and polished stones. Such aggregates scatter light in ways rarely observed in the inner solar system, hinting at origins in colder, darker places. If plasma effect or engineered shells were shaping the dust, distinct rings or bands would appear. Instead, the coma remained smooth, its polarization varying by less than 0.2% across all observed fields. The data consistently point to large, dark aggregates resembling dust seen on Centaur Pholus and small trans-Neptunian objects. The deep negative polarization and red spectral slope indicate dust that has endured millions of years in the outermost reaches of a planetary system, altered by cosmic rays encoded in complex organics known as tholins. For 3I/Atlas, the coma becomes a record of another star's debris disk, each aggregate grain preserving clues to its own formation and chemical evolution. The polarization curve signals the presence of large, irregular aggregates. These aren't compact, bright grains familiar from most comets. Instead, they are loose, porous clusters woven from organics and ice. Their structure more like tangled webs and polished stones. Such aggregates scatter light in ways rarely observed in the inner solar system, hinting at origins in colder, darker places. If plasma effects or engineered shells were shaping the dust, distinct rings or bands would appear. Instead, the coma remained smooth, its polarization varying by less than 0.2% across all observed fields. The data consistently point to large, dark aggregates resembling dust seen on Centaur Pholus and small trans-Neptunian objects. The deep negative polarization and red spectral slope indicate dust that has endured millions of years in the outermost reaches of a planetary system, altered by cosmic rays encoded in complex organics known as tholins. For 3I/Atlas, the coma becomes a record of another star's debris disk, each aggregate grain preserving clues to its own formation and chemical evolution. A single photograph snapped September 7 from the Namibian highlands electrified the astronomy world. The object glowed a vivid, almost neon green, startlingly bright against the dark sky. The photographer had expected the familiar red hue that had dominated every scientific report. Instead, the camera recorded a color that didn't belong. Within hours, the image reached professional observers. The confusion was immediate. All previous spectra had shown a steep red slope, 18% per 1,000 angstroms, matching the darkest trans-Neptunian objects. This redness was a signature of grains battered by cosmic rays, coated in organic tholins, shaped in the coldest reaches between stars. Yet in a single night, the object shone green, as if its chemistry had shifted in real time. The usual culprit for cometary green is the C2 molecule. But days before, high-resolution spectra had shown almost no C2 emission, ruling out the standard explanation. Chemists suggested other candidates, perhaps trace CN or CO, but neither had been detected in significant amounts. Some pointed to ultrafine, icy grains scattering light through Rayleigh effects. Others wondered if filter response had amplified a fleeting wavelength-specific burst. The photographer's raw files confirmed the event wasn't an artifact. Multiple amateur astronomers across southern Africa reported similar green tinge, though none as striking. Within 48 hours, professional observatories retargeted the object, hoping to catch a repeat. None did. The green vanished as quickly as it appeared, leaving behind questions. Was this a transient chemical outburst, a rare scattering event, or the first hint of a process not yet cataloged in comet science? 3I/Atlas had refused to play by the rules, widening the gap between what could be measured and what could be explained. October 3rd is circled on every mission planner's calendar. That's when 3I/Atlas will pass near Mars, close enough for the planet's orbiters to train cameras and spectrometers on a true interstellar core. Teams behind MAVEN, ExoMars TGO, and HOPE have spent weeks debating how much risk to take. Dust in the coma could threaten instruments, but the chance to resolve a nucleus from outside the solar system is too strong to ignore. If the coma thins enough, a clean image could shrink current size estimates from a 50-kilometer spread to a single number, ending years of speculation in a few frames. After the Mars flyby, the object slips behind the Sun for nearly a week. Superior conjunction starting October 21st. Ground-based telescopes will lose sight completely, a blackout window where anything could happen and no one on Earth can watch. Then Atlas reappears just days before its closest approach to the Sun on October 29th. Some researchers have floated the idea that the coma's smoothness and scale are more than just natural outgassing. What if the dust shell is a shield, engineered or evolved, to protect the core as it races through the inner solar system? There's no evidence for such engineering, but the object's refusal to fit any standard category keeps the door open for the wildest possibilities. For mission teams, the stakes are high. A clear look at the core could rewrite the rules for interstellar science. A missed opportunity might leave the object's true nature hidden for decades or forever. Its deep red color marks it as distinctly interstellar. Yet green emissions photographed on September 7th defy simple chemical explanation. Polarimetric data revealed patterns not seen in typical comets, raising new questions about its makeup and origins. Despite thorough observations, the nucleus size remains uncertain, with estimates ranging from 0.2 to 50 kilometers. As 3I/Atlas approaches perihelion on October 29th, after a close Mars pass, scientists are still debating its classification and watching for more surprises. The story of 3I/Atlas shows how even with advanced instruments and global collaboration, some mysteries persist. Its true nature and what it can teach us about interstellar visitors remains an open question.